Hello, everyone. We are the Field Programmable Gate Arrays for Machine Learning Acceleration team. My name is Milos Shashkar.
And my name is Michael Yakubov.
So a little bit of background information before we jump into our topic. To start, we have Field Programmable Gate Array, or FPGA. This is a hardware component that allows for customizable circuit implementation. Therefore, it's reprogrammable. This is really useful, and we'll talk about why that's of interest to our particular project later down the line. Machine learning, or ML, is the study of computer algorithms that automatically improve performance through training and experience. So it's similar in the way that humans learn through trial and error, and other animals as well. We design algorithms that perform the same process. Neural network, or NN, is a web of node structure used for machine learning. It's designed to improve its classification accuracy by training with data sets. So it's similar again to humans' version of trial and error. You'll continually give it different inputs, tell it what it's supposed to be getting correctly. So for example, here's a picture of a dog. The correct answer is a dog. When it guesses cat, we tell it, you messed up, try again. The next is a central processing unit, or CPU. It's the most basic hardware component responsible for processing and executing all the instructions of a computer. It's essentially the brains of a computer and one of the core hardware components. Then we also have a graphics processing unit, or a GPU, which is a hardware component that's designed to rapidly process those same instructions in parallel. It's used for graphics rendering because it can do so really fast and asynchronously, which means that you can cut down the same operations in a much shorter time. So of course, we're going to look at and examine the performance of central processing unit versus a graphics processing unit versus an FPGA. So what are our motivations for our project? So like I mentioned previously, we have our GPU and our CPU. Machine learning is typically performed using these hardware components. So for example, your laptop comes with both a graphics card and a CPU as well. And when you're running a program on your computer, your machine is typically going to use the CPU unless you use a specific library to instruct it to use the GPU. So our goal of our project is to look at what a machine learning would look like when performed using an FPGA instead, because we know that application-specific integrated circuits, or ASICs, are the best hardware choice because of the fact that they're uniquely designed to run for specific software procedures. But because of this, they're costly and difficult to make. Every single one is unique for every single different problem. The idea with FPGAs is they are reprogrammable. So we could take one that we already have, design it to work specifically for our machine learning applications, and really get to see a boost in performance compared to a GPU or a CPU, which again has multi-purpose, but doesn't work the best for every single individual use. Our methodology, we began with a simple perceptron model used to classify sonar data. So a perceptron model is a very basic machine learning model that takes in binary inputs, so zeros or ones, think yes or no, and takes a combination of these and then releases an output, either 0 or 1. And while that may sound really simple, you either get a 1 or a 0, an off or an on from an input. When you have a large set of these inputs feeding into the same output, you end up getting a pretty robust set, and you can do a lot with this binary arithmetic, as we learn later on. Next, we wrote this in Python, of course, and we deployed it on our local laptops, which use the CPU. So we got good performance from that, but we wanted to move forward on and make a proper neural network to test what was going on. So we made a simple 3-layer neural network written in Golang, which is another language similar to Python, using the C-based compiler, and we managed to get that working on our local machines as well. Instead of using the sonar data, we used a handwritten digit classifier. As you can see here, some examples of this. This is from the well-known MNIST dataset, which contains many of these handwritten images.
So on to the challenges that we faced during this project. FPGAs are much better with integer arithmetic as opposed to floating point arithmetic. So it would be beneficial if we were able to use a neural network that uses entirely integer arithmetic. One of the changes that we implemented in order to accommodate this was to use a rectified linear unit, or a ReLU function, instead of sigmoid activation function. As you can see in the left diagram, a sigmoid returns values between 0 and 1, no matter what the input is, while a ReLU returns 0 if the input is negative, and the input and returns the input itself if it is positive. The problem that this created was known as dying ReLUs, which is where all of the weights and inputs that we give the neural network ended up multiplying and becoming negative, which would cause everything to output 0, and then our neural network would basically guess 0 for everything. So here for our results, this is a diagram of what our neural network somewhat looked like. Instead of this many inputs, however, we had 784 inputs, as each of our images was 28 by 28. So 784 inputs being the pixel data. Each of those inputs then went into each of the 100 hidden neurons. This creates a fully connected neural network, as each input goes to each neuron, and it's multiplied by a randomly generated weight that we store and update as we train. And then from the hidden layer, it goes to the output layer, which outputs between 0 and 9 for each of the 9 digits. And as you can see in the bottom left, we have the training and prediction running. Took about 6.5 minutes to train and around 4.5 seconds to predict, and we got a prediction rate of around 97.32%. So the future of this project would be implementing fixed point arithmetic or scaling the values to achieve independence from floating point arithmetic. This is further implementing the integer arithmetic that we talked about earlier. Also, we would have to pre-process our input data, which is the pixel data from the images. We would do this on the CPU and then deploy this onto the neural network on the FPGA, and then compare the time between the FPGA, the CPU, and the GPU using the Rutgers iLab system. And then eventually we could move on to doing this project on more complicated classifiers like colored images and other machine learning models.
Special thank you to all our mentors. So Professor Richard Martin, Jennifer Shane, and Prasanta Navella. They did a great job of teaching us about the basics of these high barrier of entry topics. With that, if you guys have any questions, please feel free to reach out to us and we'll do our best to answer them in due time.